Compare the vast climate-controlled halls of a centralized data center with the isolated physical reality of a sensor cast inside a concrete bridge. Cloud computing operates as a distributed paradigm. It is designed to process voluminous, complex information where transmission time is not a critical factor. Edge computing forces data storage and computation away from centralized servers and pushes it directly out to the physical location where the data is generated. The specialized physical computer systems that execute this local processing are known as embedded systems. They are frequently described as small computers inside larger machines. But from an engineering standpoint, they are defined by their strict behavior, the repetitive execution of a specific single function. Creating a strict academic definition is notoriously difficult. Industry experts often rely on U.S. Supreme Court Justice Potter Stewart's benchmark for obscenity. I know it when I see it. What you see is continuous, reactive operation. An embedded system processes and responds to its environment in real time, operating exactly at the speed that environment dictates. Designing these devices requires a departure from standard software development. It demands solving a multi-dimensional optimization problem bound by strict, unforgiving physical constraints. To understand these constraints, we look at the baseline, the standard desktop computer. This paradigm is defined by its architecture. A general-purpose processor is built to deliver medium performance across a vast array of user-programmable applications, with few restrictions on size or power consumption. The embedded system paradigm is defined by its implementation. It is deeply integrated into another device, stripping away broad flexibility to achieve specialized, dedicated execution. To compare the two accurately, engineers evaluate the common denominator, the instruction set architecture, directly at the silicon level. Because the physical environment limits battery life and area, engineers must balance a complex cost function across performance, flexibility, power consumption, and unit cost. Optimizing for one variable exacts a toll on the others. This push and pull resolves into a strict linear cost equation. The discipline of embedded systems centers on finding a point on this graph that is good and cheap enough, rather than pursuing theoretical perfection. The very first major external pressure acting on this equation is time to market. Every product has a narrow window for maximum revenue, defined as 2W. If engineering runs long, we introduce D, the delay. This equation calculates the percentage of revenue lost to that delay. For a 6-month window, a 2-month delay loses 45% of potential revenue. Because the financial penalty for delay is extreme, teams cannot afford to reinvent basic logic. They rely on formalisms to accelerate design. The unified modeling language serves as this blueprint. It provides a common syntax to synchronize hardware and software development across heterogeneous teams. The second economic constraint forces a choice between non-recurring engineering cost, the one-time expense of design, and the recurring unit cost of manufacturing. For high-volume, mass-produced devices, the strategy is to spend heavily upfront. By investing in non-recurring engineering, designers optimize the physical silicon logic, which aggressively lowers the cost of every single unit manufactured. Abstract economic pressures literally alter the physical layout of the processor logic. The industry's dominant response to these strict power and performance metrics is the ARM architecture. At this physical scale, every logic gate consumes power and occupies finite area. Standard hardware floating point units consume massive silicon area and draw significant power. As a result, they are frequently stripped out of embedded processors entirely. Without dedicated hardware, a single floating point instruction executed in software explodes into a sprawling tree of subroutines, draining system cycles. Engineers solve this by using fixed-point arithmetic. They write code that executes complex math using standard integer logic blocks. This introduces severe limitations. Fixed-point math has a highly reduced dynamic range, where infinity cannot be mapped to a finite value. The system will not automatically handle overflow or round-off errors. Managing these mathematics becomes the explicit responsibility of the programmer. To regain the performance lost to these compromises without drawing more power, embedded architectures utilize data-level parallelism natively in the hardware. Single instruction, multiple data, or SIMD, allows one command to execute arithmetic and logic operations across multiple data points simultaneously. Instruction-level parallelism is also utilized. A standard ARM implementation relies on a 3-stage or 5-stage pipeline to keep instructions flowing continuously without idle cycles. High-level software abstractions are a luxury. Embedded programming requires an intimate, exacting knowledge of the silicon's physical capabilities. The industry frequently uses the term firmware to describe embedded software, but the term is slightly inaccurate. Historically, firmware described microcode written for microsequencers. It was designed as a direct, functional replacement for physical hardware on low-cost processors. Today, it refers to executable, semi-permanent software stored deeply within a read-only memory chip. Treating embedded code as just firmware written in C ignores a critical reality. The programmer is explicitly instantiating operations and directly manipulating physical hardware registers. When an embedded processor lacks performance, engineers do not swap in a faster, power-hungry CPU. They augment the existing chip with specialized peripheral computing blocks. Integrating a multiply-accumulate unit sacrifices general flexibility to execute computationally intense math tasks with high throughput. Relying on specialized hardware blocks lowers the overall instruction count. This redirects precious electrical energy away from issuing CPU commands and focuses it entirely on computation. The embedded systems engineer is an architect of constraints. They leverage custom instruction sets, rely on fixed-point mathematics, and continuously optimize multidimensional design metrics to balance cost, power, and performance. By mastering this hardware-software symbiosis, engineers successfully embed complex computational intelligence into the rigid physical limits of the real world.